Hello, I'm Yanchilina, and you are watching the channel Born Science with Firuza. Today we'll talk about what distinguishes the scientific approach from ideas that fail experimental testing. Is it easy to come up with a theory? In one conversation with my husband Vasily Yanchilin, Iosif Hryplovich, a professor at Novosibirsk University, said, "Coming up with a new theory is very easy." According to Hryplovich, his mentor and the founder of the Institute of Nuclear Physics in Novosibirsk, Gersh Butker, claimed that he could come up with dozens of theories. Whether Butker actually said this, we don't know. But the fact remains. Today, there is not a single new fundamental physical theory credited to Butker. Meanwhile, we quite often receive letters from people who claim they have created their own theory of everything. So it seems that some people really do come up with hypotheses and theories. But how scientific are they? Falsifiability is the heart of the scientific method. I've already said that any scientific hypothesis or theory must, first of all, be not only verifiable, but, most importantly, falsifiable. You can see the link to that video in the upper right corner of the screen. Let's recall what falsifiability is. It is the possibility of testing a theory in such a way that it could turn out to be false. If no such test exists, the theory is not scientific, no matter how elegant it may sound. A theory can be confirmed, that is for verifiability, and refuted, that falsifiability, but the latter is crucial. The possibility of refuting a hypothesis, falsifiability, is far more important than the possibility of experimentally confirming it, verifiability. Back in 1934, the philosopher Karl Popper wrote in his book The Logic of Scientific Discovery that the ability to refute a theory is the key criterion of scientific status. Why is this so important? Because confirmations can always be found. If you really want to, you can always pick some coincidence or some isolated observation. But refutation, that is a genuine test against reality. Let's see how this works in physics. A modern example, string theory. String theory is often mentioned as a candidate for a theory of everything. It is mathematically elegant and aims to unify quantum mechanics with gravity. However, as of today, it makes not a single experimentally testable prediction. Any experimental outcome can be accommodated by choosing an appropriate vacuum from the vast landscape of solutions. Formally, this makes the theory unfalsifiable and therefore, by strict scientific criteria, places it outside the boundaries of science. Grand unified theory, an ideal example. In the second half of the 20th century, physicists proposed the idea that the strong, weak, and electromagnetic interactions merge into a single interaction at ultra-high energies. This idea became known as Grand Unified Theory. Hundreds of theorists around the world worked on its development. Thousands of scientific papers were published. And for decades, this research program remained one of the central directions of theoretical particle physics in the late 20th century. Grand Unified Theory looked extremely appealing. The three fundamental interactions, strong, weak, and electromagnetic, mathematically converge into a single structure at ultra-high energies. This gave a sense of deep symmetry and conceptual completeness. Moreover, such theories arose naturally within quantum field theory and fit well with the already established standard model. That is why, for many decades, they were seen not as speculation, but as a logical extension of experimentally confirmed physics. However, despite decades of effort, no direct experimental confirmation of grand unified theory was ever obtained. That said, grand unified theory had one fundamental and extremely rigid prediction: proton instability. According to these models, the proton should decay with a characteristic lifetime of about 10 to the 31st to 10 to the 34th years. This prediction made the theory falsifiable. Either proton decay would be observed or the theory would turn out to be wrong. If the proton had proven to be unstable, the theory would have gained experimental support. So, what is important to understand right now? Grand unified theory shows us that creating beautiful mathematics is easy. Turning it into science is hard. Without falsifiable predictions, a theory is not scientific. Without falsifiability, any theory turns into pseudoscience, capable only of consuming more and more money in attempts to test it. With falsifiability, it becomes part of science. The story of physics shows us this clearly. Mistaken theories can be popular, elegant, and persuasive, but what ultimately matters is not the beauty of the equations and not the number of publications. Only one thing matters: the theory's willingness to be refuted by experiment. Thank you for watching this video and don't miss the next one. In it, I'll talk about how scientists search for proton decay, how much time and money they spend, what turned out to be true, what turned out to be wrong, and why this story is so revealing for modern physics. Like, subscribe, and see you next time.